In this video, we're going to go through section 10.6, which is testing a claim about a difference in means. So for this example, we're going to look at the scenario where they're answering the question, can a person train to become better at holding their breath? So an experiment was designed to find out 12 volunteers were randomly assigned to one of two groups. The 6 volunteers assigned to group 1 were given breath holding exercise to perform for 2 weeks. The other group was not given any information about the experiment. At the end of the 2 weeks, all 12 volunteers were individually tested to determine how long they could hold their breath. A researcher would like to determine if these data provide convincing evidence that the true mean amount of the time volunteers who were given the training held their breath longer is greater than the volunteers without training. Let mu sub 1 be the true mean of the amount of time the volunteers who were given the training held their breath, and mu sub 2 be the true mean of amount of time the volunteers without training held their breath. So they gave us the data in seconds. So I'm going to plot that on a dot plot just so we can check shape when we're looking at conditions of inference. So I'm just going to do that first, even though in example 1, we're looking at the hypotheses and we don't really need that information for the hypotheses. So I have 90. So I'm just going to put a dot for 90. And then 88, 70, 110, 75, and 105. For group 2, the amount of time in seconds were 40, 48, 35, 50, 55, and 62. Let's do that one a little bit. A little bit more. 62 is more over here. Okay, so what are the appropriate hypotheses? So for these, remember that we're always looking at whether something is the same or different, right? And so with a difference, that means that we're looking at, is the difference between mu sub 1 and mu sub 2 0, meaning is there no difference in the amount of time these two groups can hold their breath, right? And then they want us to figure out if the mean number of amount of time volunteers who were given the training held their breath is greater than the volunteers without training. So remember that mu 1 is the ones that were given training, and mu 2 is the ones that were not. And so that means that I want this to be a positive difference. So that means that mu sub 1 minus mu sub 2 would be greater than 0 in this test. So then we want to check the conditions for inference. So we have a randomized experiment. So we are random. So when I have a randomized experiment, the 10% condition is not applicable. So I'm putting these people into treatment groups and dividing that so that because I'm splitting them into the two groups and all of that, I do not have to check the 10% condition for a randomized experiment. So if I had 2 independent samples, that's when I would have to check, is the sample size at least less than 10% of the overall population. Then I have to check, is it normally distributed, which my data is not normally distributed. Do I have a large sample size? I do not. My sample is only 6. Remember that a large sample would mean the n is greater than or equal to 30. So I don't have normal. I don't have a large sample. The other indicator is that I have no strong skewness or obvious outliers. And if we look at the graph of the data, everything seems pretty equivalent, right? If I want to think about it, I want it to be symmetric, meaning if I were to draw a line down the middle of the data, it's pretty reflective of each other. So I can do the same thing over here, right? If I draw a line in the middle of the data, it's pretty symmetric. And so that means that it passed that condition. So yes, all of our conditions of inference were met with this data. So what we need to do to be able to find the p-value, and then this is a t-test, sorry, the p-value for a t-test about a difference in means here, we have this formula for t, where we need the mean of our data sets, we need the standard deviation of our data sets, and we need the size of our data sets. So what I've done is inputted our data sets into Desmos here. So I made data set A, data set B. The element list is giving you your values for n. So n1 is 6, n2 is also 6, because both of those data sets had 6 values. The mean of A, that's X bar. So whenever you have a repeating decimal, I would be extra careful with rounding. And so I would probably round to 4 decimal places. So we'll cut it off here and make that a 7. So we'll have 3 6s and then a 7 for that value. And then same thing with the standard deviation. So standard deviation is the S value. So S sub 1 is going to be 15.8324. So that's going to round up to a 5 there, and we'll use that value. For the second set of data, our average is 48.3 repeating. So again, we're just going to cut it off there with 4 3s. So that's our X bar sub 2. And then finally, the standard deviation for the second set of data. So S sub 2. Again, this is a 5 5. So we're going to round that 4th number up to a 6 when we're entering this into the formula and our calculators. So for this, we've got that T is going to be equal to the difference in means minus 0. So our difference in means is 89.667. And then 48.3333. Divided by the square root of our standard deviation squared divided by our sample size, and the sum of that for both of our data sets. So we're going to plug in 15.8325 and 9.8116. All over our sample sizes, which were both 6. Okay, so calculating that, it gives us a t-value of about 5.436. So looking at that t-value, we can use that to determine the p-value for our difference in means. So the value that we're going to use to identify whether or not our data provides convincing evidence that essentially those exercises work. Okay, so 5.436, I think I might have this on the slide as 5.4357. I just rounded it here. to 4 decimals because I think I have that added on the next slide. So we're going to use that to find the t-value. I do. Okay, so degrees of freedom and the test statistic are what we're looking for in order to identify the p-value or the range for the p-values. So remember that our sample size for this problem, both of them, were 6. And so notice that our formula just has n. It doesn't tell you which one to use. In all the problems for this, they're going to just give you the same sample size for both samples. So our sample size is 5. Sorry, our sample size is 6, which means our degrees of freedom is 5, which means that we are looking at the row with 5 as our degrees of freedom. Okay. Then what we're looking for is our t-value. And so we want to find the value and the placement of where 5.4357 would be. So looking in this row, it would be between these two t-values. Okay, so so our value for t is between 5.893 and 4.773. So what that means for the p-value is that it's between these two percentages, so 0.0025 and 0.001. So it's 0.25% and then 0.1% is our p-value for this problem. Okay, so remember that we have to take our sample size and subtract 1, and that tells us which row on the t-chart to look for. And then within that row, we're looking for the location of our t-value. Remember, it's not going to be our exact t-value. This doesn't work like the z-score table. Then once we find that location where it would be, that gives us a range of p-values that we can then use to make a conclusion about our test. So the last example, we're going to look at that p-value and compare it to an alpha to make a conclusion. So does the data provide convincing evidence that the true mean amount of time the volunteers who were given training held their breath is greater than the volunteers without training? So the p-value that we got from the last problem is it's somewhere between 0.0025 and 0.001. Notice they didn't give us an alpha. So if there is no alpha in the problem, you're going to use that 0.05. And so remember, way back at the beginning of this semester, they've been using that 5% as a confidence level to make a conclusion if something is statistically significant or not. So if something provides me evidence that, hey, this can't just be by chance, it's got to be something's wrong with my original thought process here. So this has less than a 0.1% chance of happening by chance alone. So this value is less than alpha. Remember that when the p-value is less than alpha, that means we are going to reject the null hypothesis. That means that the true means are not the same. So that means that there is convincing evidence that the true mean amount of time for volunteers who are given the training held their breath is greater than the volunteers without training. Okay, so if I were to have gotten a value that was greater than alpha, then I would fail to reject the null, which would mean that there is not convincing evidence the true mean is greater for those that were given the training. So remember that these two things are opposite. So reject is negative. There is convincing evidence is positive. So if I were to switch it, fail to reject is positive, is not is negative. Okay, so that's all for testing a claim about a difference in means.